All right, today we are adding vectors. Super exciting. Okay, so kind of our main question today is how can we add vectors? How can we subtract vectors? How can we quote unquote resolve vectors? And you might be watching this going, what the heck's he talking about even with a vector? Because I've kind of forgotten, but we'll go back to that as well. A couple of words, which is one of them on there is a vector. And the other one we'll be looking at later is a resultant. And I'll probably be going through this pretty quickly. So pause, rewind, take whatever notes you need as you go through this. So as a reminder, what a vector is, it's a measurement that's got magnitude and direction to it. We'd contrasted this with the word scalar. Something that's a scalar only has magnitude only. And this was like when we did speed or we just did distance. So that did not have a direction to it. So what we're looking at now is the things that do have a direction to them. Not sure why that got so much bigger. Don't really need to see me anyway. I'm not sure. All right. I'll resize myself. There we go. So vectors have magnitude and direction. So this is when we talked about velocity. Velocity was a vector measurement because it had an amount and it had a specific direction that we needed to go into. Right? A lot of times when we're talking about vectors, we represent them by arrows, and these arrows show both the magnitude and the direction based upon how long the arrow is and obviously in which direction it goes. We'll use vectors throughout the year. Right now we're talking about motion, so vectors can represent motion. Later we'll talk about forces and they can represent that as well. So vector would just be like what popped up on the screen. It's an arrow. So the size of this arrow would give some information, the direction as well. So we use varying lengths that tend to indicate the magnitude. So the greater the number, 10, 20, 30, 40, the longer the arrow is going to get in relative amount. So if we were comparing two lengths, a length of a measure of 20 should have an arrow that's twice as long as something that was a 10. Seems kind of obvious, but sometimes we don't know these things. And the direction tells us the direction. If it's pointing up, then that could be up or north or a number of different things. If it's pointing to the right, it could be to the right, it could be to the east, it could be forward. But a lot of times we'll actually need to specify things. So you might see a larger vector versus a smaller vector. These would have the same direction, but this would be a larger magnitude than the smaller one. Looks like it's about twice as big. And so whatever number accompanied this would be about twice the smaller vector. So sometimes we can change the vector around. So if I've got an amount and it's represented by this vector A, then think about mathematically what happens if I wanted to say 2A. That would be doubling the vector. So if we drew it, it should be twice as long, which would still be going to the same direction. However, if we made it negative A, it would be the same magnitude, but it would be in the opposite direction. Arrow would just kind of switch its ends that we would have on there. Oftentimes the shorthand is when we write a vector like A or B or C and we're indicating it, we would end up putting an arrow over the letter, and that lets us to indicate that we do have a vector of some type like this. So a B, or C with an arrow over them are a vector. Now the arrow this over the letter doesn't indicate the direction. As you can see, none of these arrows are going, none of these drawn arrows are going in the same direction as the arrow that is on the letter. But it's just our shorthand formatting of how to indicate that you've got a vector. All right. So if we had a question, which vector has the largest magnitude, that's going to be B because it's the longest arrow. So when we're talking about magnitude, we're just talking about an amount. How much do we have? What would negative B look like? Well, negative B would be the same as B, except the arrow tip would just get switched around. So we wouldn't have the arrow on this end. The arrow would simply be on this end. So negative A would point this way, negative C would point this way, and the other end would just be with no arrow. So again, direction is kind of a big deal with vectors, and we can indicate that direction by the way the arrow is pointing. And if we wanted the arrow to go the other way, we could indicate it as a negative vector. And we could also double it. So again, if I wanted to double C, then it would take this line and just double the length of it. So that's mathematically, if C equaled 10, then 2C would be 20. Therefore, the arrow representing C would need to double in size for it to be equal to 2C. Okay. The other vocabulary word we had was a resultant. Now, resultant is simply the sum of two or more vectors. Oftentimes, when things are moving, they don't just have one force acting on them. So, for example, if you had a toy car that was moving in a north direction across a walkway, but that walkway was actually moving itself, kind of like you might have at the airport or at the aquarium where you have a moving sidewalk type of thing, we end up that the car is not really, if you're an observer, the car is not really moving north and it's not really moving east. It's actually moving in the northeast. And so we put these two arrows together. So there's a vector to indicate the speed of the car, there's a vector indicating the speed of the walkway, and the resultant vector is the one that takes both of them into consideration. You can kind of see what happens here is that we start with the resultant vector is going to start at the very beginning, and the resultant vector is going to end at the very end. And it's just going to, I won't say give us a shortcut, but it's going to give us a resulting magnitude and direction that takes the other two into account. Right. So our next question is, how do we add and subtract vectors? And today we're just going to be drawing them. All right, so eventually we'll be talking about the mathematics that go along with this. But again, it's pretty simple. When you add vectors graphically, we're going to align the vectors from head to tail. So you're going to start with one arrow, and then where one arrow ends, the next arrow needs to start. We don't change the direction of the arrow. Whichever way the arrow is drawn for you, that's the way it needs to be drawn. So we can move them around, but we can't twist them and change the directions. And we're not going to make them longer unless we're told to as well. So we're going to draw the vectors in order. We're going to match up the point of one arrow with the end of the next to indicate the overall direction. So again, if we have these vectors A, B, and C, we can kind of start seeing how they fit together. So if I wanted to put vectors A and C together, we can think about what that would look like. So the rules were take the vector and we're going to draw it out. And again, it would need to go in the same kind of direction. I'm not going to be able to draw very well on here. I'll just leave the A the way that it is because that's my first one. If I'm adding C to it, I need to draw an arrow that looks just like this. It's going to start where this one ends, and it's going to go and be drawn just like C is. So basically, this is A, and this is C being put together. And then by definition, our resultant vector would be starting here and ending it over here to show where is my overall displacement and by how much do we have. Right. So let me, whoops, go back. So if we put A and C together, we would have a better picture that looks like this. And then if we added the resultant vector into it, again, the resultant vector is represented by this green line or this green arrow. And this green arrow is what happens when we put A and C both together. And so that green one would be the resultant vector. So we have some motions going in this kind of northwest direction. We have some motions going more in the southwest direction, and it's a little bit larger. So if we put all those together, we could predict where the overall motion would be going with this thing. Right. So let's look at a few more of these. Well, one of my first questions was, does it matter which goes first? And the answer is no. It doesn't matter if you started with A and then added C, or if you added C and then put the A on it. And you'll see how this kind of works. So if I'm not, see if I can draw the C out so it sort of looks like it should. So if I draw the C arrow first, and then I draw the A arrow afterwards, something like this. It's not very good. I made that one a little bit too long. So my resultant would start at this dot and it would end at this arrow. And you can see if I put them together. Now it looks a little bit different, but the direction of my red arrow is about the same direction as this green one. It's off a little bit because I can't draw very well. And the length of it is about the same as the length of this one right here. All right, so if I draw A plus B together, then again, follow our directions. I'm going to take the vector of A, draw it out, stick the vector of B, and we'll put the beginning of B onto the arrow. Got too much stuff up here. Keep moving it in the wrong place. So this is vector A. And then with vector B, we connect it to the end of vector A. And then the resultant vector is the one that starts at the very beginning and ends at the very end. Okay, so it's pretty simple. Again, does it matter which one you did? No, if I started with B and added A, then, so if I started here and drew, this is vector B, and if I added this A vector to it in this direction, so this would be my end point, and this would be my starting point, and if I connected them, if I drew everything perfectly, this resultant vector in between, which I'm trying to sketch out, this resultant should be the same as this one in terms of length and in direction. You can see that it still should be going up, and it's approximately the same length. So it doesn't really matter which one you start with. Your resultant vector should be the same length and in the same direction. If we want to do A, B, C, we just piece them all together. So start with my A, and then where A ends, B should start, and then where B ends, C should start. And if we put all of those together, we should get something that looks along the lines of the resultant coming this way. So vector A is at the beginning, vector B, and then vector C. Again, would not really matter if you drew C first, then B, then A. The resultant vector should still be green. It wouldn't make the same shape, but the resultant vector itself would be in the same direction, the same length, although it wouldn't look exactly the same for the rest of it. If we wanted to draw 2A minus B minus 2C, I think we have to manipulate these a little bit. So 2A would simply mean I need to double the length of this first arrow. If I do negative B, that means I need to flip the B arrow around so that it goes in the opposite direction, because that's what the negative says. And then if I did a negative 2C, that kind of puts both of them together. I need to flip the arrow around and double the length of it. Once I had all that done, I could simply just connect all the arrows together. And once we connect all the arrows, we should get another resultant that looks a little bit like this. So I've got my 2A, which was to double the length here, minus B, I flipped the arrow around to the other direction, and negative 2C, I flipped the arrow and then doubled it. So my resultant vector would be from the very beginning of all the drawings, at the origin to the very end. And again, this resultant vector would have a magnitude and direction as well. Eventually, we'll start giving them numbers and directions, but today we're just drawing the stuff out there. So vectors have magnitude, they have direction, and we can represent this by drawing. And so these arrows represent the size and the direction of the vector. And then if we have multiple vectors, multiple motions, multiple forces, we can put all of those together to create a resultant vector, which would show the overall combined motion that we have there. All right, I'm going to end this.